I think we can start. So welcome everybody to our knowledge exchange meeting on energy and nutrients from manure. In this event, of course, we do not have the ambition of exploring the whole topic because it is quite a large topic. We would need a series of seminars for this. So we are just, let's say, giving a focus starting from the, let's say, the claim with which we advertise this event, that manure is energy and nutrients. So it is really not something that should be seen as a waste. It is something that it should be exploited at the most, according to the existing technologies and the economic conditions in your context. Of course, we cannot, as I said, explore the whole topic, but we can give you a focus on some existing technologies according to the experience we have. This event was, let's say, co-organized by me, Federico Dragoni, as being in charge of the thematic area of manure storage and spreading in the Climate Farm Demo project, and by my colleague Anders, who is in charge of the biogas production thematic area of the Climate Farm Demo project. So, what else? Maybe I can also briefly introduce myself. I'm a postdoctoral researcher at the Leibniz Institute for Agricultural Engineering and Bioeconomy in Potsdam. Anders, do you want to say something?
Just briefly as well, Anders Johansson. I work for a small company in Sweden called AgroVast. And AgroVast is a cluster organization with the aim to improve farming. To keep it short, we initiate and lead projects leading to new methods, new technology, and other ways to support rural businesses in west of Sweden. Yep.
Thank you. Okay, the group is still quite small, I must say. I don't know why, because many registered for these events.
Federico?
Yes?
How many people are in total?
We had 85 registrations, so I'm quite surprised.
In the room, I think. Do you have some problems with the limit? No.
Yeah, we have a limit of 100. That's why we made, let's say, to be on the safe side, a limit of 85, because there could always be some extra people.
Okay.
But we are still a little bit low. I think it's better if we start or we will finish late, and we will accept people while they are coming. Okay, for the ones that are here, we prepared, let's say, short survey. The idea is to, let's say, know each other, and also for us to have some, let's say, kind of report of who is joining these kind of events, and know if we were successful in circulating it, in advertising it beyond the Climate Farm Demo project. These events are arranged usually in collaboration with the sister project, the Climate Smart Advisor project. So you can join the survey by accessing the website app.sli.do and entering the code you see here, or just scanning the QR code. Can you see the answers flowing to the poll?
Yes, we can.
Okay, so it's not many answers, but we can see that we have a nice attendance from people that is not part of the two projects, which is interesting. And of course, we have people from Climate Farm Demo, which is let's say, expected. Okay, more or less an even, let's say, attendance, half and half, can roughly say. We can move to the next question. What describes your profession best? So just to know if we are mostly researchers or farm advisors or other categories. Oh, we have one other. Would be interesting to know what does other mean. But we have, let's say, mostly researchers. A few more people joined in the last second. I don't know if they will make it to participate to the poll or not. But we have some farmer advisors and consultants, which it's, let's say, the main ambition of the seminar. So it's good to have them on board. Okay. I think we can conclude the poll. Then let's go to the agenda of the event. After a brief introduction, we will have a presentation of Dimitrios Tiris, who managed the Rest for Life project, and his presentation will be, let's say, the introduction of our online seminar, as he will mostly focus on the general topic of renewable energy for livestock farms and for farms in general. Followed by a presentation from Lukas Vanasek on existing technologies for biomethane use in livestock farms. Followed by a session of questions and answers. And then we will have the second part of the presentation. Let's say the ambition of the event is to combine the energy uses of manure, showing some examples, of course, starting from the biogas technology, rooted in the biogas technology, and then transition to the nutrient use of manure and digestate. And this is the second part, where I will present really a few things myself, just a few things, and then give the floor to Thomas with a presentation on mostly on nutrient recovery technology and biogas related technologies, and then a presentation from Gunnar.
Yes, and Gunnar is the founder of the company EcoBalance, and he will talk about nutrient and carbon recycling and their concept to refine biogas, digest it into to improve nutrients use, efficiency, optimize nutrient composition, reduce nitrogen losses, and so on. That's the fourth part of the presentation.
Okay, thank you. So the usual rules, I guess we are all familiar with this, but just to keep in mind that the online seminar is being recorded and the slides will be shared. So we all have to agree about the fact that we are recording. If anyone does not agree, please let us know. It's Climate Farm Demo rules. It is, let's say, an actual important deliverable of the project to have these recordings in place and allow the participants to get them from the cloud folders. And as a general rule, please keep your microphone muted during the presentations. This may not be valid for let's say for the speakers. We can be a little bit flexible, and of course there will be questions. So during the questions, you can either enter your questions in a written form so that we can read them, or you can ask vocally, verbally. as I said, questions will be allowed. There will be a Slido for the questions, so you can enter there your questions, but you can also, let's say it, raise your hand and ask. In the Slido, if you see any questions from the others that are of interest for you, you can always upvote the questions and let's say, in this way, give your preference for this question and we will give it priority. Okay, this said, I can give the floor to the first speaker of the day, that is Dimitrios. Dimitrios, the floor is yours.
Thank you, Federico. Hi, everyone. Many thanks for the invitation. My name is Dimitrios Tiris, and I'm a PhD candidate in the Agricultural University of Athens. I will provide a brief presentation of the Reservoir Life project activities, which was officially concluded last month, actually by the end of September. So you can see the slides changing, right? Perfect. So how everything started, since intensive livestock farming is one of the most energy consuming subsectors of modern agriculture and mainly based on fossil fuels, and at the same time requiring a large amount of electricity and thermal energy to cover strongly diversified energy demands. It appears to be necessary to a crucial aspect that EU should address to defossilize livestock production to achieve a more sustainable livestock production. Here is where the Reservoir Life project fits. Reservoir Life, as I mentioned earlier, was a Horizon 2020 project with 7 partners from 8 EU countries, proposing a solution for the replacement of fossil energy use by utilizing renewable energy sources. A combination of technologies and solutions was installed and evaluated in 4 livestock farms across Europe. The solutions were demonstrated in 4 different farms: 1 experimental swine farm in Belgium, a commercial swine farm in Italy, an experimental egg production farm in the Agricultural University of Athens premises, and in 1 experimental, let's say, dairy cattle farm in Germany, where the biogas-related technology was installed, and for which Lucas Vanasek will provide a more detailed presentation. I will start by introducing you to the main technologies, the main systems developed and showcased in the framework of the project. We had photovoltaics and thermal photovoltaic panels, heat pumps, borehole thermal energy storage systems,
Dimitrios?
And all of it?
Sorry, I think we lost connection for a short while. I couldn't hear you.
Okay.
Very short while.
Okay. Now? Perfect. The technologies that were developed and showcased were the following: photovoltaics, thermal photovoltaics, heat pumps, borehole thermal energy storage systems, biogas to biomethane upgrading units, retrofitted tractor for biomethane use, and all of these together were communicating with the help of smart control systems. This provides us the opportunity to develop cost-effective and case-sensitive solutions towards the goal of fossil-free livestock farming. Next, I will provide an overview of the interventions made in its pilot farm, beginning with the experimental swine farm, Vilvo, in Belgium. Vilvo is comprised of two interconnected buildings, hosting sows, piglets, and fattening pigs. There was no cooling system, and the heating was provided via a gas heater and mechanical ventilation. In this facility, we installed a 2-in-1 multi-source heat pump to cover the necessary thermal loads, and the PVT system to partially cover the energy needs of the farm, both in thermal energy and electricity. The heat pump, as I said before, was 2-in-1, providing both, combining both a high temperature heat pump and a low temperature heat pump. The one was used for domestic hot water and heating, the high temperature one, and the low temperature one for floor heating. The thermal photovoltaics that were installed on the roof provided, besides electricity, thermal energy, let's say hot water stored in a tank that was used to make the operation of the heat pump more effective, more efficient. A dedicated room was where a room was dedicated for the installation of all these systems, with the heat pump that you can see, and the solar station that was handling the hot water produced by the PVT system. Next, we have Golinelli farm, the commercial swine farm in Italy, where interventions in 2 buildings were made. The one that we present here is the system installed in the nursery barn that hosts around 2,500 winners. And there, the LBG boiler was replaced by a heat pump that covered the thermal energy needs of the whole facility. In order to increase the COP of the heat pump, also PVTs and geothermal storage was installed. As you can see from the schematic, we have the solar system that produces hot water that it is stored in the geothermal storage, and it's the heat pump that can harness both energy from the ambient and energy from the geothermal storage. This is another diagram showing the flow of the heat of the hot water from the PVTs to the borehole thermal energy storage, and then to the heat pump. These are the photographs taken during the installation of the technologies. And next, we have Agricultural University of Athens, where we have a small experimental poultry farm. There are it is a 2-space one, hosting both pullets and hens. Before the project, only forced ventilation was used to remove the thermal loads during the summer, and some thermal lamps for the pullets during their first weeks. Here we installed the heat pump that regulated the indoor space conditions, and also PV panels were installed to cover part of the total energy needs of the farm. Some other interventions were also made, like the installation of LED lighting for the for the needs of the animals, and of course the smart control system for the communication of all these units. Here you can see the heat pump and the PVT system installed outside the building. The PV is in a nearby roof, and some of the readings that we acquire in real time through the smart control system. And now, finally, we have LV80 farm in Germany, where an existing biogas digester was utilized in order to feed a biomethane upgrading unit that was developed in the framework of the project. An existing a diesel tractor that was already on the farm was converted in order to use biomethane. And other interventions included thermal photovoltaics and the smart control system. The overall goal was to utilize mainly the produced biomethane as well as the PVT's production to reduce the total energy consumption of the farm. Here you can see the PVT system that was integrated in between the heat recovery milk cooling system and an electric water heater. The thermal energy produced and stored provide us the opportunity to reduce the electricity use of the water heater for the production of domestic hot water to the farm. And finally, I think the intervention that is more relevant to today's topic. Here you can see the biogas plant that was already installed and operating on the farm. And in the left of your screen, in the right side of the screen, you can see the installed bio-CNG unit equipped with a filling station, as well as the adapted farm tractor for biomethane use. On farm, we have now a bio-CNG production capable of producing 10 cubic meters per hour with an average methane concentration of above 97%. This biomethane is used for the tractor that operates about 3 to 5 hours daily, consuming something less than 6 kilograms of bio-CNG in daily basis. Of course, these interventions, the operation of the system was monitored and evaluated, assessed in different levels. Here we will have a look of the results related to the environmental and economic performance. I'm sure that Lucas can also elaborate further on that. The environmental assessment results show an enhanced performance in general. You can see in the diagram on the right side of your screen the difference between in the single environmental score before and after the interventions about the concerning the on-farm operation of all systems. In the table, you can see the values used to run our models for both the bio-CNG upgrading unit and the biomethane farm tractor. I have to note also that the produced biogas from the biogas digester used to feed before the reservoir level interventions a combined heat and power unit for power generation. Now it feeds both the CHP unit and the bio-CNG unit. These are the values used to run our assessment that was based mainly on the performance of the operation of the systems during the first year after their installation. Here you can see also that we have enhanced environmental performance when all these systems are working together. We have an indicative yearly operation of the combined system of CHP, diesel tractor, and before the interventions, and after the interventions, we have the operation of the CHP, bio-CNG plant, and the bio-CNG tractor. As you can see, for this indicative year, the environmental performance is considerably enhanced. Finally, the economic assessment of the intervention, so that we have for the bio-CNG unit alone, we have a discounted payback period below 10 years, that with the use of subsidies would be much lower, around 5 to 6 years. The bio-CNG farm tractor, if is considered in combination with the bio-CNG unit, would give us a payback period of 2 years, even without the use of subsidies. For the combined operation now, even though we an enhanced environmental performance is observed, we have a bit of deteriorated economic performance compared to the reference systems, the reference system, because of the high investment cost of the bio-CNG unit, as well as its operation. The economic performance, though, would be enhanced if different operation scenarios are investigated, including different ranges of hours of operation, as well as energy cost and selling prices. Of course, higher capacity of a bio-CNG unit could perform much better, and this is something that is was investigated in parallel with RES for Life project. Concluding, what the project tried to achieve, the impact that tried to create was to provide advanced, cost-effective renewable energy technologies for the sustainable operation of livestock farms, providing in some cases enhanced thermal comfort for the animals. We believe that increased productivity in livestock farms can be achieved with minimum climate change impact. And this is something that needs further investigation in order to create more knowledge in the sector. In the EU, something that would lead to increased competitiveness of the livestock sector in EU. That's all from my side, very briefly. Many thanks again, and let me know if there are any questions that I could answer. Thank you.
Thank you very much, Dimitrios. I would go straight to the next presentation, and then we have a question and answer sessions right after Lucas. So possibly there will be questions also for you then. So Lucas, now the floor is yours.
Thank you, Federico, and thank you also, Dimitrios, for the nice overview of the whole project RES for Life. So, to my person, I'm Lukas Vanasek, and I'm more than 10 years in the field of biogas and biomethane, and more or less an expert on it, also with agricultural related things in combination with the green energy from biomass. Next. So I want to give you now in deep look on the task of the biomethane from the RES for Life project, and to the idea. This idea came up to handle in the project because so far there was no solution available on the market for farmers or for on-farm production that could make at an economical, feasible way the on-farm bio-CNG fuel production. So that was the idea, to integrate this task in the RES for Life project, and it was named Adaptation of a Biogas Upgrading Kit, especially for biogas coming from manure of livestock farms, with a focus on its cost effectiveness at the medium and small scale. In the end of the project, the task was so successful that we gained the highlights from the European Innovation Radar. And now, next. And now I want to show you the overview about especially this idea about the task. So in general, the idea for producing on-farm bio-CNG fuel is to defossilize the agricultural and forestry sector. And in this project, we see that there is a very, very large potential to do it with rest, with food and feed rests from the agricultural production. On this slide, you have an overview about the biogas and biomethane cycle. Like it is done in combination with the biogas process with farms. So first of all, you have the harvest, you have agricultural byproducts, you transport it to the well-known biogas facility, you have to store it over the year. In the end, you have a mixture of at livestock farms of feed rests, of manure, of slurry. If you have the possibility, you also got organic waste from the food and feed industry, and all this project can be treated in a biogas facility to the well-known biogas, which contains 50% of CH4, methane, and 50% of CO2. And in this task, we will focus on In this task, we will focus on the bio-CNG filling station that didn't existed on the market so far in a very small scale, like we see here. Next. And before we go into technical details, I show you the background of the genesis of the idea. So we gained so far not a lot of knowledge since 2007 at an Austrian biogas facility, which is a very big, huge biogas facility. And since 2007, out of a research project, there is a bio-CNG filling station in operation. But the problem so far was that this bio-CNG station on the picture here, it was too expensive for an on-farm, small-scale bio-CNG filling station for tractors. Next. And so we tried to gain knowledge how to make this process smaller and more reliable for farms. And we extracted the technical things that could bring down the costs to an economical feasible farm filling station. And this also was done by retrofitting tractors to CNG operation and testing the whole units over more than 10 years. Next. And also in this genesis of this bio-CNG idea, we had to inform policymakers and organize the kart race or some public events to bring this bio-CNG topic closer to the people. Next. Now I finished the overview of the idea, and before I go now into the technical details, I want to show you the video which shows the retrofitted tractor and the bio-CNG filling station now gained in this Rest for Life project. Yeah, you have here the biogas facility, tractor. Now we are at the pilot plant from the farm filling station. The retrofitted 100% bio-CNG tractor. Former retrofitted tractor only could use 60 to 70% of bio-CNG, and the rest have to be diesel. So now we have a retrofitted 100% bio-CNG tractor in the Rest for Life project. The filling process, and now ready to work, refilled. This is the next slide. No, one back. Yeah, sorry. Thank you. Thank you. So now to the technical details of this task. So we designed out of the knowledge we gained from the bio-CNG plant in Margarethenmoos, we designed in the Rest for Life project a very small scale, simplified process that brings down the cost like 50 to 70% compared to so far on the market available common plants. The design process is a full closed gas circle that has a compressor, a chiller, then active carbon filters to remove the sulfur, heat exchanger to dry the gas, so they put the water out, and in the end, a hollow fiber separation membrane that separates the gas from the CO2 and the CH4. And the CH4, after the separation, is compressed to 250 bar, and then in the bottles you see at the top, the gas is stored at 250 bars and ready to fill in CNG vehicles like tractors, trucks, or cars. Next. The technical characteristics of the micro BNG plant, which was designed as a pilot in this Rest for Life project, is the compressor you see on the picture can treat 10 to 12 cubic meters of raw biogas per hour, and this leads to approximately 4 cubic meters of concentrated CH4 at 97% of purity per hour, and that means you have 4 kilograms of fuel produced here per hour. Like mentioned before, the plant you see here is a one-step closed circle membrane separation process that produces an off gas besides the fuel with 97% off gas with 80% CO2 and the rest CH4. And this gas is pumped back to the digester and burned in the parallel driven CHP on this biogas facility. So you have this this full closed circle where you do not emit any CH4 containing gases to the atmosphere, and you don't have to care about that issue on this fully closed gas circle power plant. Yeah, and as you see here on the picture, the upgrading facility is thermal insulation insulated open frame container. That means you don't have rooms that are closed, and you don't have the problem with explosive sounds with this design here. And one filling process of a tractor or a car takes approximately 5 minutes. Next. And now especially a focus on the novelty, as on the key findings that were done here with this pilot plant to bring down the costs and the complexity of such a plant. And so it is a very simplified and compact design. We only have here a one-stage membrane permeation process instead of a three-stage membrane permeation process that was common so far for such plants. We have, like mentioned before, no direct emissions, CH4 emissions to the atmosphere. And one key technology we implemented here was the hybrid compressor that have a three-stage compression process. And the first stage of the compressor is used to clean the gas at approximately 8 bar from biogas to purify CH4, and the step 2 and 3 of this piston compressor compresses the gas to 250 bars. And like mentioned before, we have here an open frame, no closed zones or rooms that can to avoid explosive sounds that would bring other problems, technical problems with them. Next. Here a picture of the hybrid piston compressor. You see the big piston at 8 bar that makes the pressure for the gas cleaning, and left and right from the big piston on the right picture, the two smaller pistons for the 250 bar compression to produce the CNG fuel. Next. And here we have now the data that we gained via the monitoring process of the pilot plant. So we see that we can clean and high compress one non-cubic meter of bio-CNG fuel with an energy consumption of 0.94 kilowatt hours electrical energy. The separation process in the hollow fiber membrane can be done at a comparable low pressure. That means here we work with a pressure of 9.8 bars, and common plants work at so far on the market available common plant with 3-step membrane separation works at 14 bars. So we came down in the monitoring phase of the pilot plant down to 7.8 bars. That helps us to reduce the energy consumption. The separation temperature of the membrane separation CO2 CH4 splitting is 57 degree in average. The methane concentration we gained in the pilot plant at the end was 96.7%. So that's the fuel quality. And also interesting for the practical operation is that the one startup of the production plant lasts in average 26 minutes, and it's designed to start up the plant once per day and fill up the gas storage bottles. Next. Now to the costs and to the economic aspects of such a plant. So you see here the overview of the possible fuel costs for this small farm filling stations. So we have comparable high fuel costs with our small pilot plant we see on the pictures from the Rest for Life project here. The 10 cubic meters plant, and we come up to 2.25 euro per kilogram with that size. And we see here we came down with costs. The cost degradation starts at 35 cubic meters per plant and goes down to 1.5 euro per kilogram with the little bit bigger plant with the 35 cubic meters per hour, and comes down to 1.37 euro per kilogram with a plant that can treat 65 cubic meters per hour. And you see here, it have to be mentioned, the 10, the 35 and the 65 cubic meters plant all fits in a 20 feet container, so they are at the same size, only the compressor is bigger, and due to that fact, you have a very, very fast cost degradation above 35 cubic meters per hour. And so a common solution for farms will be the 35 cubic meters per hour plant, like we see here from the economical side. and the investment costs of such plants starts approximately at 300,000 euro. Next. Now, at the end, we have I have some figures that show you the potential of this technology. Related to livestock farms, we can say one cow produce 289 non-cubic meters biomethane per year. That results in 208 kilogram bio-CNG per year, and it's an equivalent of 400 car kilometers. So with one cow, with the manure of one cow, you can drive 4,000 kilometers with a car. When related to field waste, so 1 ton of wheat straw produces 250 cubic meters of biomethane, which is equivalent of 3,600 car kilometers. Next. And to the agricultural farming process, related figures that show the potential. For example, 1 hectare of plowing needs, with the shown bio-CNG tractor from the Rest for Life project, for example, 25.5 kilogram per hectare, so the plowing. And that means with the manure of 1 cow per year, you can plow 8 hectares of arable land. Next. So I finished the technical details and the economically figures, and we think with this invention, with this farm peeling station, we have the opportunity to defossilize broad field of the agricultural and forestry sector. We offer a production unit for farms of bio-CNG. We bring down the CAPEX, OPEX costs with this pilot plant from the Rest for Life compared to market available solutions so far for small fleet size, and we are sure that we can gain bio-CNG at costs of below €2 or 1.5 euro per kilogram of fuel. So thank you for the attention, and questions are very welcome.
Thank you, Lucas. So I would now open the floor for questions. Questions. If you have any question, you can enter it in the Slido, as we did at the beginning for the, let's say, initial survey we carried out, but you can also just raise your hand and ask. We have an approximate, I would say, 5 to 10 minutes for questions, depending on also on how the debate develops, and then we will have to move to the next topic. We also had a little bit of a slow start, allowing all the participants to slowly flow in the meeting room. So I can expect that we will possibly finish like 5-10 minutes later than expected. If nobody has questions, maybe I can start sparking the discussion with, let's say, a question that possibly Lucas can answer, but it is open also to Dimitrios, open also to Thomas, because he contributed to the project as well. And so, well, first of all, a comment, as you say, I really think that this technology is something that was missing. It's something novel. I mean, biomethane upgrade existed already, but this technology really brought it at a smaller scale, a scale that possibly didn't exist before. You mentioned a fleet of few cars, few tractors, so it really seems to adapt to the scale of a regular livestock farm. But in terms of costs, when I think, for instance, of the price of regular fossil fuel, it is still lower. Possibly also because there are no taxes on it, and this would immediately raise a very sensitive topic for the farmers, especially in Germany. I know that the taxes on the fuel have been quite a debated issue. So my point is, what do you see coming in the future for these technologies? Do you expect the costs to further go down, maybe according to the increasing adoption of these technologies? Or would you expect rather the fossil fuel prices to go up so that your technology becomes more competitive? What do you expect for the future?
Yeah, thank you for that question. And we have to say to summarize the costs per fuel unit. I will say 1.5 euro per kilogram of CNG fuel is feasible at the moment. So it's feasible now of a green 100% fossil-free fuel. That means the CNG fuel contains also more energy than diesel than diesel at a factor of with 1 kilogram of bio-CNG you can replace 1.3 liter of diesel. That you have to keep in mind. And the other thing is that green fuels like green bio-CNG or green diesel, if there is existing technology in the future, can gain this greenhouse gas quotes if the well-known discussion about the greenhouse gas quotes that are used by non-fossil fuels in vehicles, in the transport or in the mobility sector. And this monetary advantage of the greenhouse gas quotes is not taken into account with the 1.5 euro per kilogram. So with this technology of 100% green fuel, fossil-free fuel from agriculture, I see the monetary advantage for farmers to gain also monetary benefits from greenhouse gas quotes. So you have it's a huge difference between fossil fuel and green fuel, and in this transition phase, like over the next decades, the green fuels will have the advantage of this greenhouse gas quotes, I think so. And at some point, if we have then 100% of green fuel on the whole world, then it will end up at the final price. And yeah, but I think this the advantage. We can not only look at the production costs, because the fossil gas is available without the production step. You only have to put it out from the ground, and so it's but this is fossil with the climate effect, and here we have produced green fuels on farms on site that is non-fossil. So with the maybe the monetary aspect, the advantages you can gain with the greenhouse gas quotes, they're already existing for green fuels.
Okay, thank you, Lucas. I think in particular the clarification about the heating value of methane is important, because essentially you are lowering the numbers you mentioned by roughly 30%, as I understood correctly. So the real cost for the farmer will be lower.
If you compare it with diesel,
with diesel,
you are like 1.2 or something.
Okay. I have one question from the audience. Maybe it's simply easier if I allow you all to read it. And the question is, who are the main stakeholders you need to engage with to set up a biomethane plant, and what are the main challenges for those stakeholders? This seems to be, again, a question for you, Lucas.
Yeah, the stakeholders. So when I catch the question right, the stakeholders are for small facilities like we showed here in the Rest for Life task are farmers. That farmers or a conglomeration of if you're very small farmers, then a conglomeration of, for example, 10 farms that build a biogas facility together and make out of this biogas facility then electricity, heat, and fuel for their own needs, or also for feeding of the electricity to the grid. This could be a possible setup of stakeholders for this small scale plant. So the farmers and like also the farmers, or maybe at the end small companies that have trucks, Spedition or something that are close to the farms that can use the fuel.
Okay.
So this,
if I try to see this question from another point of view, because I'm thinking, for instance, trying to be on the boots of a farmer. A farmer wants to do this, and what are the challenges for a farmer to set up such a plant? Besides of the economic aspect, of course, he needs to have the money for the investment. But do you see any other challenge? For instance, in terms of policy, regulations?
You mean political policymakers as stakeholders?
Yeah. Or simply regulations, yeah.
Yeah, we discussed the greenhouse gas quotes, and from the policymakers, from this regulatory institutions, there would be the necessity to make it possible for the small plants to participate at the greenhouse gas quote market, like in the same way like the big facilities. So you have to decrease the administrative barriers to make it possible for small plants to participate at the greenhouse gas market. That would be necessary to have this advantage on the small. It's especially necessary for such small plants, because it cannot be that the small plant cannot take part at the greenhouse gas quote market, and the big plant is possible to do it. So that have to be solved, this problem, for political on the regulatory point of view.
Yeah, I fully get your point. I get your point. So thank you for your answers. I think we now need to move on to the next presentation. But before introducing you to Thomas, I have two slides, really few slides, because we mentioned as a topic in the. Thank you, Lucas. We mentioned as a topic in the agenda of the event that we also wanted to stress how manure management affects the biomethane potential of manure. And I brought you two examples from a study carried out here at our institute. Here you can see that the biochemical methane potential, so the potential methane production from, in this case, dairy cattle manure, is affected by the storage time. So the fresher is the manure, the higher is the methane you can get from it. Of course, it is logistically not possible to have fully fresh manure as we obtained manually for our barn samples, the blue dots in the chart. But you can see that the degradation is not that fast. It is noticeable, let's say, in some weeks or months. But of course, very old manure has a lower biomethane potential, and it can be, let's say, related to the lower dry matter content, the lower content of volatile solids, and most of all seems to be related to the degradation of cellulose and hemicellulose. This does not only affect the total methane you can get, but also the rate at which you can get the methane, which is particularly important for commercial plants, because commercial plants are not batch reactors. They need to, let's say, obtain the methane from the given substrate according to their residence time. So the faster is the process, the more, let's say, profitable is for you. Similar observations, but even more significant, were obtained for swine manure. Here, similarly, we had a decrease of the volatile solids over time and of the volatile fatty acids too. That seems to be attributed again to the degradation of hemicellulose, cellulose, but in this case also the degradation of raw fats. But here you can see that the difference between fresh samples and samples of manure from the outside storage, the outdoor storage, is particularly striking. But of course, we also have to think that according to how the typical pig barn is made, the samples will likely never be completely fresh, because the manure is typically collected in a pit below the barn. But again, time matters. So the logistics of the manure collection for biogas plants, biomethane plants, would abate methane emissions to the atmosphere and increase the potential, the biogas potential for your plant, if the delivery of the manure is, let's say, timely. This has also an environmental relevance. It's not just about economics, because the methane that is not emitted, let's say, in the plant is emitted to the atmosphere. But now I would give the floor to Thomas, who will go on, let's say, in this perspective of energy conversion of manure to biogas, and also address the topic of the nutrients recovery from manure. Thomas, the floor is yours. You have slide control. Thomas?
Thank you,
Yeah.
Federico, for the introduction. Yeah, Thomas Ammann is my name. Just to some aspects on my profession. I'm here leading the department Sensors and Modeling, and also heading the research and livestock research, and I have the professorship Environment Animal Relationships and Interaction at the Freie University in Berlin, and the veterinary science there. And in the past I did some intensive research, as it was already mentioned, on biogas and also on slurry separation. So I would be pleased to give you some aspects on what we have found out in the past on optimize the nutrient cycle. So if we have biogas and other treatments, so we have the possibility to improve the nutrient efficiency in terms of having a better nitrogen, phosphorus efficiency in the plant production. So in this way, first to see some literature, if we look to in the whole system, and we look to the to the slurry untreated. The slurry is a mix of liquid and solid. It's not really liquid, it's not very solid, but it is pumpable. And it has a lot of carbon and it had a lot of dry matter. And this creates some challenges if we have untreated slurry. If we look to the storage phase, for example, we see these red boxes. We see if you have as lower as the dry matter content in the slurry, as lower is the energy input for mixing. All the time we have to mix before spreading. As higher the dry matter content, as higher the energy pervasive for mixing. If we look to the nitrogen emissions, it's also the case. If we mix, then there is an enhanced nitrogen emissions during mixing within the storage period. Further in the chain, if we look to the spreading and after spreading, we see also a negative influence of the dry matter content. As higher the dry matter content, as higher the ammonia emissions after spreading. And if you look to the soil, also here the carbon has an effect in nitrogen incorporation in the soil. That means as higher than the carbon in our slurry, as higher the danger to incorporate nitrogen in the soil. That means no direct control on a direct efficiency of nitrogen in the plants. So that's as the figures I show here, they are quite old figures, and in the meantime there are a lot of literature that supports these arguments. So for this basic background for us, then it is clear to have a liquid which is reduced on carbon and dry matter content. And this is exactly what the biogas pretreatment do, and also what a slurry separation do. So there are some examples on slurry liquid separation. They sometimes and often also combined with biogas plants, especially with biogas plants Lukat introduced. They use biogas plants, they use residues. They have also some undigested material in the slurry and so forth. That it makes sense to separate the digested. So some figures out of studies of mine in former times for slurry liquid solid separation. Here we see the nutrients, and we see the mass, 10% of the mass goes in the solids. More than 40% of the dry matter goes in the solids. More than nearly 50% of the carbon goes in the solids. That proves the hypothesis that if doing biogas and doing a separation, then we can improve the value, the efficiency of the manure. In case of, for example, the nitrogen carbon ratio is going down in the liquid phase, so that makes it more calculatable, more direct usable for the plants. Just to underline this, I would like to show a picture on that. This picture I took around 15 minutes after spreading, and we see here a slurry which is untreated. So the slurry had a dry matter content of around 10%. This is the same field at the same time. The difference is there is a dry matter reduced, as it is done by separation or also by biogas plants. And 30 minutes, 15 minutes after spreading, we do not see any liquid on the surface. And this is the phase where ammonia volatilization takes place. And the nitrogen goes down in the soil and has higher ammonium content, and so the plants can take off the nitrogen directly. So this is the effect in general, to have dry matter reduced slurry, which gives us by doing biogas, for example, or also doing solid liquid separation. So now Federico is, yeah, okay.
Sorry.
Again. Yeah, Have to also, sorry, there is some, yeah, here we are now. Just to see, we have further looking also in the, if we have dry matter reduced slurry, how to spread this slurry. And there are a lot of research done in the meantime to see the effect of bringing down the slurry near the soil or to spread it wide. And we see the difference. There are some results from our research, and a lot of colleagues do have the same results. What we can see here is that the ammonia volatilization takes place in the first hours. What there is lost, it's lost forever. If we have dry matter reduced manure and we spread these dry matter manure close to the soil or even incorporated in the top layer of the soil, we can then reduce the ammonia emission after spreading dramatically. So pre-treatment and spreading are the challenges and are the needs to have a nitrogen efficient system in general. Then what is have a look to the solids. Here we see this is actually the plant Lucas introduced us in Utzeneich, where the CSP plant is produced as well, and the farmer there, they have a very successful biogas plant over more than 15 years, and heat some separation as well. And what we can measure is that we see around 25% dry matter are in the solids. And in the liquid phase, we have then a reduction of from 10, let's say, to 5 or even 4 or 3% dry matter in the liquid. And the separation productivity, so the separation throughput is around 15 cubic meter per hour. Then is the next question, what do with the solid? Okay, we have a possibility to make compost, high value compost of it. Bring this high value compost as a soil fertilizer, let's say, and together with the liquid phase, it gives us a optimum management also in the fertilizer aspects. Otherwise, looking more to the bioeconomy aspects, there is would be a possibility to dry the solids, as we have in some cases heat available from the heat and power plant, for example, and there is a dryer, an example of a dryer that gives the possibility to dry the water out of the solids and further on to use these dried materials for pelletizing, for example. And this is what the farmer did at that time. He dried the solids and produced pellets out of it, and these pellets are really on the market, a high quality pellet for gardener, private persons, for gardening, etc. So to improve the bioeconomy aspect in that perspective as well. Just that finally, one aspect, we all know how the biogas plants look like. I would like to focus your attention on one aspect. It deals with how to store the digestate. And if you look in the practical situation, we often can observe that the storage tanks are open. And if we consider in the manure, there are higher ammonia concentration, and we have the wind turning over this storage, and then is the door opening for losing ammonia as well. So for this is important to cover also the storage tank. For this, this is an example. For example, for existing biogas plants, I had the honor to coordinate an EU-wide project called EU AgroBiogas, and within that project we developed together with the colleagues with our colleagues in Italy an system afterwards. This gives the possibility afterwards to cover the storage tanks and to close the the tank or to the gas bearing system. So if there also existing methane emissions coming out, they will be used in the CHP, as we see here. So yeah, if we see 20 years back and we see today, so we started with a CHP 25 kilowatt, let's say. Now we have 500 or even more 1 megawatt CHPs. So it gives us an idea how this biogas topic developed intensively in the past. Then this is a challenge to use the heat. We have no opportunity to lose the heat. So when there is a CHP heat and power coupling on farm, then it is probably connected with a heat grid, or to use heat using utilizations, for example, for grain drying or wood chip drying. It's also the plant Lucas mentioned us where the CHP was produced. So this just to give some examples how to improve the nutrient cycle by optimizing the nutrients in the slurry, and also by optimizing the technique in terms of covering the nitrogen in the system as much as possible. So we can summarize that biogas and separation processes, they are efficient techniques, not only firstly to produce energy, but also to improve then the value of the nutrient and to close the nutrient cycle. It's important to cover the storage tanks, and it's also important to bring the slurry right after spreading direct to the ground, so that the emissions can be not happening in that way. And it's also important to applicate the slurry and the digestate, if it is possible, in growing crops, so that the nutrient can directly go to the plants, and there are some techniques available to do this as well. Although the weather is important, no wind, if it is cool, and as I said, also it is possible and effective to incorporate the slurry into the topsoil. That's what I like to say in short words. So if there's some aspects for discuss, I'm available. Thanks.
Thank you, Thomas. So we are now approaching the conclusion of the event. I think that Thomas' presentation was particularly good, let's say, in having an overview of the biogas technology and how the biogas technology is deeply rooted in a circular livestock farm, enabling the let's say the most efficient use of nutrients. And also, let's say, in connecting this with the perspective of the energy valorization of the manure, that is not disconnected from this. In most of the plants, we have heat produced, and this is unfortunately still not exploited in the largest possible way. I know many plants in which the electricity is sold as renewable energy, and the heat is not exploited. But we know that there are economic and regulatory challenges for this. But now I would give the floor to the next speaker, and to do this I have to allow him to get slide control. Just a second. Okay, Gunnar, please, the floor is yours.
Thank you, Federico, and thank you for the opportunity to present how we work with digestate, even though we are close to the end of the webinar. All right, so I come from the company EcoBalance, which I started in 16 years ago. We develop technologies for the recycling of nutrients in nutrient-rich residues, such as digestate, sludge from wastewater treatment plants, etc. Different technologies and solutions for that. So to summarize these, we started out with a phosphorus extraction technology to extract phosphorus struvite from wastewater treatment plants mainly. We have developed the technology to extract nitrogen, ammonium nitrogen as solid ammonium sulfate. That's a unique technology. A lot of other technologies available where you get the nitrogen as liquid ammonium sulfate. When we have it in solid form, the opportunities are much more. We have much more opportunities than when liquid. We have technology called EcoS for drying and pyrolysis of sludge, where we remove cadmium in the process. So that's specific technologies. And then we have more complex solutions where our technologies are integrated. For example, the digestate refining concepts that will be the main topic of discussion today. So solutions that we work with are adapted to residue properties, market options, and local circumstances, because and this is important. You have to be flexible in order to get value for money. I should also say that I have a background as a researcher from Lund University. I'm a plant ecologist, and my field of expertise is plant nutrition, basically. Okay, so one thing that we really have to remember is that when we recycle nutrients or when we fertilize, we have to keep in mind how nature actually has evolved over millions of years in terms of how plants access nutrients. This is what nature is adapted to, including the plants that grow for crops. So if we do something that's very different from this, we can't expect to have the same kind of efficiency as in a natural system. For example, we a lot of times we spread a lot of slurry or digestate in one specific moment in time, often when plants are not developed so that they can access these nutrients. Not very strange that we got a lot of losses. Better would be if we could spread the nutrients adapted to the point in time when plants really have the possibility to use the added nutrients. Yeah, and then, digestate is a mixture, as Thomas said, of solids and liquids, and that makes it difficult to handle, and other things happen with it as well. So just to say, it's complete plant nutrition. In that sense, it's really good option compared to, for example, artificial fertilizer, which is often just nitrogen or a little bit of phosphorus and potassium, but it's very diluted and a mixture. So that makes it challenging to work with. So it being diluted means that we have a high consumption of diesel for transport and distribution. It's not really a good alternative to transport it for more than a few kilometers, because then very soon you get into very high cost for transport. Driving with heavy equipment causes soil compaction. This is a big problem. We already do a lot of things on our farm fields with heavy equipment that causes compaction. So reducing compaction, which does lead to lower revenue in terms of lower production. We have to do something about that. We can't keep on driving with yet larger tractors all the time. Spreading with high doses and often at the wrong time causes nutrient leakage. As I said in the beginning, we spread a lot, often early in season. Plants doesn't have the capacity to take up the nutrients. Not very strange that we get losses. The high pH, major problem. After digestion, we most often have a pH above 8. This is very good conditions for ammonia volatilization. Especially if we spread it when it's in hot weather and in sunshine. We can lose most of the nitrogen actually. And the nitrogen to phosphorus ratio is also a problem. In Sweden, we have the maximum of 22 kilograms for phosphorus per hectare a year as a threshold. We can't spread more. Different limits in other countries, but given that the nitrogen phosphorus ratio is quite low, this means that the maximum phosphorus threshold leads to that we cannot use more digestate than as much as we would like to satisfy the nitrogen demand. We still, when we have spread maximum in terms of phosphorus, we still have a high nitrogen demand, and we can't use the digester that we have. That's a limitation. And there's also limits to spreading in growing crops, depending on what we grow. Finally, greenhouse gas emissions. Digestion means, benefiting organisms that produce methane in anaerobic conditions. When you take out the digestate of the digester, that doesn't mean that they stop completely. You still have production of both methane and laughing gas, strong greenhouse gases that will continue to emit during storage, and that's something that we have to take care of. So major problems: complete plant nutrition, good stuff, but challenging. Okay, so our concept for digestive refining. we start out with the watering, and that's much more than taking out the fibers. I'll come back to that. And after that, we dry the solids. And so we go from digestate with perhaps like 5% dry solids into, after the watering, we get 30% dry solids, 25 to 30, depending on material and the watering technique. And after drying, we get up to 85 to 90% dry solids. So what happens with nitrogen and phosphorus when we do this? The organic fraction, in the dried organic fraction, we get about 30% of the nitrogen and 90% of the phosphorus. And this is nitrogen in organic form. The ammonium nitrogen goes to reject water, or the liquid that comes out of the watering. Sometimes also called centrate. About 70% of the nitrogen, the bulk of the ammonium nitrogen, a little bit of the organic, and less than 10% commonly of the phosphorus. So all the phosphorus basically to the solid organic fraction, and the majority of the nitrogen to the liquid reject fraction. And this, of course, means a great difference in terms of nitrogen to phosphorus ratio, and then in turn on how you can use this material at spreading and fertilization different times during the season. So there's reject water. What can you do with that? Well, we can use our extraction technologies to get the little phosphorus that's in there out as struvite, but more importantly, to extract the nitrogen as ammonium sulfate in solid form with our technology. And then we can add some external nutrient source if you would like, and we can use these different solid forms and combine them into different solid fertilizer products. And that's where most of the phosphorus and 30% of nitrogen goes. So the reject water, what can we, and this includes also basically all the ammonium if we extract it. But we can do something else as well if we have this process on site at the farm or close to. So instead we can, water to reuse, that's just the leftovers. What we also can do is to acidify the reject water and use it in fertigation. Because it can become stabilized and we lose almost no ammonium nitrogen if we acidify. We can, after acidification, we can also concentrate it with evaporation. Most of the time we really need large-scale installations for that to be cost efficient, but it is a possibility, and use that later, mix it up with water in fertigation system. So different options. So the watering compared with defibration. A lot of times when we talk about separation, we mean defibration, taking out the fibers, but that's just all the small particles will remain. So in the digestate, we have the nutrients, they are separated into very coarsely described into large particles, small particles, and dissolved material. And the small particles, this is important, that's where you find most of the phosphorus. Very little dissolved, very little in large particles, so small particles. So if you don't take out the small particles, you still have the phosphorus in the liquid phase. So defibration, taking out the fibers, you still have a nitrogen phosphorus ratio of approximately 7. This is just as expensive to acidify as a slurry or a digestate before separation, because the organic matter inside here buffers against acidification. And also, the acidification is not stable. The organic material will decompose, and then the buffering capacity goes up, and pH will increase again. So it's a poor use of money to acidify without a proper dewatering beforehand. The fiber fraction that you get at is approximately 35% dry solids. In dewatering with flocculation, on the other hand, this is a different story. Flocculation, that means that we add a polymer, a flocculation agent, so that the very small particles are bound together in flocks that can be separated with the dewatering machine. It's not the same as a defibration machine. Now, when we take out the small particles, we can change the nitrogen-phosphorus ratio so it goes up to approximately 30. This is very important if you have a maximum threshold on how much phosphorus you can add. So if you have a nitrogen-phosphorus ratio of about 30, there is basically no limit to how much you can use in terms of mass, and you can get all the nitrogen you need. Also, when we have taken out the organic material, including the small particles, we get a material that's much cheaper to acidify, and it will also be stable. It doesn't buffer, and pH will not increase over time. It will stay at the level we acidify to. Another thing that's very important when we take out particles, including the small ones, we can use this water in an irrigation system, so it becomes a fertigation system. And that gives us possibilities so that we don't have to drive with a tractor and heavy equipment on, on the field. So I'll come back to that. The water fraction, we get approximately 25% dry solids. It's not possible to get it as dry in the dewatering step as just the defibration, and that depends on that we have in the flocks that we dewater. That they hold some water. We can't press harder because then we destroy the flocks. This is technology, the watering technology, very well developed in the wastewater treatment sector. They've been doing that for decades, and it's basically the same technology. You just change a little bit on how you work with flocculation for it to work with digestate. Okay, so ammonia volatilization. We have talked a little about this already. This is a study in Sweden, spreading on ley. And you can see here that you get a lot of volatilization in the hours after spreading without acidification, but you get a reduction of up to 95% of volatilization if you acidify the material. So big difference. This is not reject water. This is just the slurry as it is, but acidified and spread directly, so you don't get the buffering I talked about. So acidification has a large potential in terms of ammonia efficiency. So if we combine all these numbers that we have on how we do handle nitrogen in a conventional solution compared to another, then the next step, I'll just sum it up here. So we start out with a slurry with 100 units of nitrogen. After digestion, we still have in the digestate down at the right corner, we still have 100 nitrogen. We don't lose basically anything in digestion. In storage, it says below storage, it says export 20 nitrogen due to excess phosphorus. Now this is for Swedish conditions. We can't spread more than 22 kilograms of phosphorus per hectare a year. That means that we can't use all the digesters that we would like to. So we have to export 20. So we lose 20 compared to if we had lower phosphorus in the material that we want to spread. We also lose some nitrogen in the storage as ammonia and laughing gas. And this is when the storage is covered. When the storage is not covered, we can easily lose half of the nitrogen. Half. And that's what happens. Very poor nitrogen economy. So in a situation where we have a cover storage, so after that step, and that we have to export some, we can still spread about 70 units of nitrogen from what we have from the 100 we had in the beginning. So at spreading without acidification, we have to calculate that we lose approximately another 20 units. It can easily be much more than that if you spread at the wrong time. In the summer, hot weather, sunshine, easily you can lose a lot. And then since we spread a lot at the same time, and the plants don't have the possibility to take it all up. When we spread a lot, we get leaching losses. There's no way around that. We do get that. Another 50 nitrogen approximately. So remaining for the crops to take up is only 35. It says 65 nitrogen there, uptake 65N. That's wrong. It should be 35. Sorry about that. Wrong in this picture. So only 35 remaining from what we had from the beginning. That means that if we want to have a balance in this system, we have to add 65. We had 100 from the beginning. We have spread only 35 to the crops for the crops to take up, that they can take up, and we need to add another 65. So, and this is a common problem. You don't really calculate a lot of effect from the organic the slurry that you have. So a lot of farmers, they know that they have, without doing the calculations, they know that they have a poor efficiency, so they add on artificial fertilizers, just without thinking so much about it. We can do so much better. Okay, so in an optimized nitrogen economy, still digestion, in the dewatering, we sort of lose, or short time lose, 30 nitrogen units to the solid phase. And we can you do a pelletized product of that. We get a nutrient liquid or reject water down at the right-hand corner that we can store. Now, if we have a cover storage and we acidify, we will not lose any nitrogen storage. So we get a storage stable nitrogen nutrient liquid with 70 units. In fertigation, we don't lose anything either, because when we are down at pH approximately 6.5, the ammonium loss is very small. It's so small that we don't have to calculate about it. So for the crop to take up, we still have 65 nitrogen for uptake. That means compared to the conventional system, we only need to add 30 or 35, but in the conventional system, they needed to add 65. So this it's a great improvement in terms of nitrogen economy. And given the volatile artificial nitrogen fertilizer prices, it's quite a good idea to optimize your nitrogen economy in this way. And quite easy to do. This is not rocket science. It's quite easy. Okay, fertigation. Well, basically you use ordinary irrigation systems. This a ramp system where you spread it out on row crops. And these are systems that they work with themselves. You don't have to pull them with a tractor, so you get the good benefit of not having to drive with heavy equipment on the fields. This system could be used for cereals. It could be used even in for grazing areas. So this is one possibility. Another one, which is very interesting, is autonomous fertigation machines. This is one developed by an American company called 360 Yield Center. It's called 360 Rain. You see there is a roll with a hose on it. So and there's also a small diesel engine on it. So it goes autonomously by itself. It follows a GPS line that you set out in the computer program so it goes out. So the hose is fully developed, and then it goes back with the hose, and then it takes another turn. A very good change with this compared to a tractor with somebody sitting in the tractor driving it is that you don't need people on the machine. It works 24/7, and this means also that you can shorten the period in time when you do the actual fertilization very much compared to when you must have people that cannot sit on the tractor 24/7. So the very large possibilities with this. You can use this machine also for untreated slurry or digestate, but then you don't get that advantage with the change of nitrogen to phosphorus ratio. So the dry phase then, as I said, we dry it. We can also add in some nitrogen there, as we did in this case, producing these pellets and pelletize. And then we get a material that we can use at the same manner as artificial fertilizer. For example, at sowing together with the seed, which we have tried out successfully in several different types of machinery with this material. So in this case, if we want to have a nitrogen concentration in this material that's competitive, then we need to add nitrogen from another source, because most of the nitrogen, remember, in the dewatering went to the liquid phase. So as we lost so much nitrogen in terms of the solids, so we need to add some from another source, and that we can take, for example, from wastewater treatment plants with our EcoN process. So we get a solid ammonium sulfate, 21% nitrogen, high nutrient plant availability. Basically, you can spread it as it is, but we see it as raw material for fertilizer production. So combining digestate from household waste, manure, slurries, whatever, with ammonium sulfate and maybe a little bit of struve if you like, we can make these circular soil health promoting fertilizers. So with our technologies, we can both make the most of the liquids on site, and we can use the solids to produce a competitive fertilizer for other markets or for use at another time. Okay. That was my last slide, so thank you, and I'm open for questions.
Thank you very much, Gunnar, for your very clear and inspiring presentation. I think, let's say, it was helpful to stress and further advance some of the concepts highlighted also by Thomas, in particular that the manure is still active. So it is actively losing carbon in form, especially of methane, volatilizing ammonia, losing laughing gas, and all these losses are generally not properly accounted for, and let's say force the farmers to maintain a very inefficient system. But there is room for improvement, and in this online seminar we only had the ambition to, let's say, show you some options, and without, of course, having the possibility to explore them all. But I think this is something that we should definitely consider, possibly for future seminars, dedicated maybe on single topics, some of the topics we had in this seminar. So we are already a little bit late. I would approach the end of the seminar. Meanwhile, I circulated in the chat the instructions for some remaining questions, to put remaining questions in the Slido. But I'm checking, and I do not have any question for you in the Slido. I would invite the people to raise their hands in case they have questions. Otherwise, we can go to the conclusions. So no questions. I would just ask you for a little bit of patience for a final feedback on the event, and especially not only questions and feedback on this event, but also proposals for topics for new events on the biogas team and on the manure spreading and storage team of the Climate Farm Demo project. If you have any proposal or anything in particular that you would like to discuss more in depth in future events, you can let us know by entering your preference in the Slido you can see here. The Slido, I think we can keep it open a little bit longer than the end of the event, so that you have time to think about it. Is there any other comment, maybe from you, Anders, or remark from any of the participants?
No, not really. I think we had some interesting topics here, and as you said, Federico, we can probably dive a bit deeper in future seminars. But please let us know in this Slido if you think that's a good idea.
Okay, then this said, I would like to thank you all for joining the event, and most of all, thank our speakers for their inspiring presentations. Thank you, everybody, and we can always keep in touch in case you want to contact base with us. Please let me know. You have my email details, and I guess also contacts with Anders. So, thank you for joining. Goodbye.
Thank you. Bye now.
Thank you. Thank you, Federico.
Thank you.
Thank you, Dimitrios and Lucas. Thank you very much.
Thank
Thank
you.
you
Bye.
for the organization. Thank you very much. Yeah. Bye bye.